Hello everyone, it's great to be here. I'm Antti Karjalainen. I work with Codenomicon, which is an information security company based in Finland. And last spring it was that we stumbled upon the Heartbleed bug, and I'm here to talk about how it was discovered. It gets a little bit technical, but bear with me. I hope you find it interesting. So how the Heartbleed bug was found. A little bit background. Codenomicon develops fast testing software, and usually when we are developing new test suites for some new test network protocols or file formats or stuff like that, we usually test our test suites against open source implementation so that we can be assured that it interoperates with actual implementations of the protocols. And at the same time, as a byproduct, we come to fast test also those open source implementations. And if we find something there, we report them upstream. And so we are also helping the open source community at the same time. So what fast testing is, it's about automatically sending anomalous data to the target system. SUD is system under test, so it's target system. And usually file formats and protocol implementations are fast tested because in those cases you cross the trust boundary, you take data from some untrusted source and process that. So those are, from the security point of view, the interesting cases. Also, APIs and graphical user interfaces, for example, can be fast. But this is about information security. Fast testing doesn't require access to source code, so it can be also tested, used for testing proprietary software. Codenomicon has a history about nearly 15 years, over 15 years. And during those years we have found quite a many open source vulnerabilities, but I think Heartbleed is the most known one. So how we discovered Heartbleed. What's interesting to notice is that Heartbleed wouldn't have been found merely by fuzzing, because usually when you are fuzzing, you are monitoring for crashes in the target system. But Heartbleed was more subtle because OpenSSL handles heap quite peculiar way. They have this gotcha between the heap and the OpenSSL. So it didn't actually cause crash. So what we were needing was a more sophisticated test oracle that could recognize the Heartbleed. And we had 3 dudes working on this TLS, and Riku Hietamäki was developing safeguard features, which are those more sophisticated test oracles. I was adding those safeguard features to our existing TLS fuzzing tool, and also I was adding new test cases, new protocol extensions, so that we can trigger more bugs in the TLS libraries. And then we had Matti Kamunen, who was testing our test tool against OpenSSL and GNU TLS. Those safeguard diagnosis methods are, for example, certificate validation. So what we are doing, we create anomalous certificates and check if the target system accepts that, and give a fail if it actually accepts it. Same goes with the authentication credentials. We fuzz anomalous credentials and test if the target system is accepting them. Then we give warnings if the target system is for some reason accepting weak cryptography algorithms. And what is interesting in this case is the unexpected data check, which detects if we are receiving more data than we should according to the valid case. So I was adding those safeguard features in the TLS test suites and also implementing Heartbleed protocol support in the TLS. It's an extension used in DTLS and TLS, and I think on DTLS it is used more often because it makes more sense there, because DTLS is used on top of unreliable channel, and then there you have to check whether the other peer is still there. So you send this heartbeat message, and if it comes back to you as it left, then the other peer is still there, and you can continue the communication. On TLS, it is used for keeping the connection alive. If for example, messages are exchanged rarely, so then there can occur timeouts, and Heartbleed is for keeping the connection alive. And the use of Heartbleed extension, like any extension in TLS, should be negotiated during the TLS handshake. And TLS handshake looks like this. It is initiated with client hello and server hello response with its certificates, and that way authenticates itself, and session key is exchanged and ciphers are put up. And then there is application data, and also these heartbeat request response message pairs can occur during that application data exchange. And when the session is closed, close notify alert is sent by server or client, and the other peer should respond with a close alert too. So what was the test case that drew our attention? We were analyzing client alert message, that last message of the sequence. And this is the valid message, so content type there is 1.5. We put there 1.8, because our fuzzer now knew the heartbeat protocol, so it tries different content types in this case. And what happens was that we were receiving varying sized responses. It wasn't the close notify we were receiving from the target. It wasn't this kind of 2-octet payload. There is 0100, which should be the close notify message. We were receiving varying sized responses, and when we decrypted the payload, we noticed that it is actually sending a heartbeat response message to our close notify, which shouldn't happen. So what we learned is that actually that close notify alert message, it is a heartbeat request message where the first octet of the 16-bit payload is 0. And what we thought is that OpenSSL takes the second octet of the length field from its memory and dumps that amount of memory back to us. And that way it is varying, because that second octet of the length can be anything between 0 and 255. So next logical step was to try a crafted heartbeat request, which would request the maximum amount of heartbeat payload from the target system. And what was happening, it actually dumped 64 kilobytes of its memory content back to us. And along in all that memory content, there was practically everything. What we were seeing was certificates, and that notified us that this is something serious, because it isn't just plain zeros, for example, or something like that. There is actually some memory content in the payload. So what it is that makes the Heartbleed so bad? I show this first. So what was in that memory content that was leaked? There were private keys, session keys, basic auth credentials, and any kind of credentials. emails, instant messages, credit card numbers. Correct me if I'm wrong, but that's quite private stuff. So it's the content that you want to encrypt in the first place, and all that stuff was leaking. And what made it even more dreary was that OpenSSL was supporting the DTL heartbeat protocol by default. It is very rarely really used with TLS, and in web world you don't actually need a heartbeat protocol for anything, really. So it shouldn't be there by default. And what was another aspect was that OpenSSL didn't require the negotiation of the heartbeat extension. So this means that you could actually send the heartbeat request during the TLS handshake. You didn't need to exchange the session keys and authenticate your client or server before exploiting the Heartbleed. So it meant that default OpenSSL installation or deployment of the library was supporting the heartbeat protocol, and it could be exploited during the TLS handshake. And the market share of the OpenSSL is quite huge in the web world, because Apache and Nginx is using the OpenSSL library, so it was very bad. And also, attack leaves no traces, so when you try to mitigate from the Heartbleed, you cannot say if you have been exploited. So what you needed to do was to revoke your certificates, because it might be possible that you have compromised your private key and reissue the certificates. And after that, all the user credentials need to be updated. And of course, before all that, you should patch the OpenSSL library. So that was Heartbleed.
Wonderful. So let me open the house for questions.
Here's some questions also for you. You can check them.
Yeah, we'll share the presentation. Yes, anybody questions?
So there are numerous fuzzing tools available for network protocol fuzzing, right? So for instance, Sully, etc. So, but what are your thoughts around fuzzing mobile applications?
Well, if the mobile application is supporting some protocol or supporting some file format, then we create anomalous message feed or protocol PDUs and send them to that application and see what happens.
Yeah, but just mobile input. So network protocols and files are relatively easier. But what about fuzzing input to mobile applications?
Well, it's hard to do automatically that kind of. Maybe emulators are a good environment when you can just fuzz the graphical user interface. But from the information security point of view, that isn't that interesting, because what is interesting is the stuff that comes from the untrusted sources. Mobile apps are here, so you can trust yourself. But of course, fuzzing is always making software more robust, so it makes sense to fuzz also the graphical user interfaces, for example.
Were you set out for finding the Heartbleed? Were you aware that there is something called Heartbleed available and you are discovering that? What was that? What made you to go to that level?
So he's trying to ask, like, did you get any kind of hunch that there's something in SSL?
No, not at all. It was actually a normal procedure for us to test open source targets. It may occur some vulnerabilities there or may not. But either way, main point is to test our own software, our test tool, that it keeps interoperating with those systems. And in this case, we just noticed that this is something extremely critical.
So that means this OpenSSL vulnerability exists since inception, maybe 5 years back, 10 years back, and the data could have been compromised in last 10 years?
It was actually 2 years ago. It was New Year's Eve 2011 that the commit was made, which actually added the Heartbleed protocol support in the OpenSSL. So it was about a little bit over 2 years that the bug existed there. But I think it didn't get caught before this is that I think OpenSSL is fuzzed all over the world. It is so commonly used library, so it is quite well tested. But the Heartbleed protocol is rarely used, so it hasn't get that much attention before this.
Wonderful.
And now that we had automatic tool that detected this, it is possible that we had triggered that even earlier, but we didn't have means to detect it automatically because it didn't cause crash. But now that we have this new test oracle with Codenomicon, that we are.
Wonderful. So we have the next speaker. Yeah, just one moment, please. Yeah, just one moment, please. We have our next speaker. Sorry. Naveen Mehra. So Naveen, may I request you to just get things ready? So if you would come over, we'll have your question now. So we can do some parallel processing and save some time. We are running late.
Mr. Antti, I'd just like to know how this was fixed. Was it fixed by the modifying the Heartbleed response, not to pick the contents of the heap and do some other kind of padding or something like that?
No, it was fixed by sanitating the length because OpenSSL did know the length of the record. And if the length of the record says that payload size is 2 octets, or in this case 3 octets, and inside that payload, that Heartbeat request says that this includes payload of 64 kilobytes. So it's just comparing those two, whether they are making sense, or it was just length sanitizing. It's very basic operation when you do this kind of software development. You should. Yes. It was fixed by sanitizing the length field. And if that is not correct, that length field, then send the alert message back and close the connection. But I think it hasn't been corrected that the Heartbeat protocol is still used during the TLS handshake. So I think that is also one aspect that needs to be corrected in the OpenSSL library. Because it doesn't make sense that you are making systems, that kind of systems vulnerable which doesn't use the Heartbeat protocol. From the security point of view, that doesn't make any sense that there are this kind of features that you are not using, but they still are causing your headache.
So one last question, and the answer can be very short. In fact, it's just a number, that is, how many more 0 days you and your team have discovered, and is probably part of your responsible disclosure process, but it's not known to the rest of the world. So how many more 0-day vulnerabilities do you and your team have right now? No, I mean which you have discovered and you are part of the process of doing the responsible disclosure.
I have been working on TLS and TTLS protocols for a year now, and during this year we have been something like between 5 and 10.
So 5 and 10, it's only you? 0 days which you have right now?
Our test people, those are
okay, your team. So you got 5 or 10 0 days right now with you, which the rest of the world doesn't know.
Well, they have.
Very good.